Okay guys, let's finish up chapter 3, and what we're going to do today is we're going to talk about fluids, and we're going to talk about gas laws. And we're going to start with fluids. We're going to talk about the pressure of fluids, we're going to talk about the buoyant force, and we're going to talk about when fluids are in motion. So let's go ahead and talk about the pressure. Fluids exert pressure evenly in all directions. And we talked about this on the last video. We were talking about that the water particles are exerting pressure and they're colliding with the wall of the water bottle. And so the fluid is going to exert pressure evenly in all directions on its container. Now let's go into buoyant force. Buoyant force is the upward force that keeps an object immersed in or floating on a fluid. Let's dive into that a little bit more and give you an example that would make more sense. At the ocean, you have fish. The buoyant force of the ocean water equals the fish's weight. So that means the fish is suspended in water. So if the buoyant force equals the weight, because we're going to learn later in this semester that weight and force are the same thing. So if the buoyant force equals the fish's weight or something else's weight, then it's going to be suspended in water where it can go around in the middle of water. Now, a shell in the ocean. The buoyant force is less than the shell's weight. So the shell ends up sinking to the ocean floor because the shell's weight overpowers the buoyant force. Now, a seagull can actually float on top of the water. I'm sure you've seen that before if you've been to the beach. So that means that the buoyant force of the water is greater than the seagull's weight. So that means the seagull can float. So anything that's less than the buoyant force can actually float on top of the water. Now, the person that came up with how to calculate buoyant force was Archimedes. That's just some information. I believe it's in your notes. You don't even have a blank for it. But I just wanted you to understand buoyant force a little bit more. So fluids, all type of fluids, even other fluids that are not water, they all have buoyant forces. And depending on how strong their buoyant force is will determine if something will be suspended, sink, or float in that fluid. Now let's talk about fluids in motion. Fluids move faster through small areas than they do larger areas. And you're going to get to see an example of this in a simulation in just a moment. Viscosity of a fluid depends on particle attraction. So let me give you an example. If something is very viscous, it does not flow very easily. An example of that would be honey. Something that is not very viscous, like water, is going to flow very easily. So viscosity is the resistance of a gas or a liquid to flow. So if the particles in a substance are really attracted to each other, then the substance is going to flow slower. So in honey, you know, it's thick and it flows very slowly. The honey particles are very attracted to one another, so they stay together longer and don't want to flow very fast. If the particles in a substance are not really attracted to one another, then it's easier for the substance to flow faster. This is our example of a fluid in motion. Now, these are not things in the water. This is just showing you dots, like pretend like they're water molecules, because if I remove the dots, you'll start to see that you can't really see that the water is moving, right? And so the dots kind of give you a visual of how fast the water is moving. So let's bring the speed down, the speedometer, and let's see how fast this is moving at this moment. So it's moving 1.6 meters per second. Now, do you remember we talked about that fluids move faster through small areas than they do large areas? So let's change that. Let's make this pipe smaller. I'm going to try to pull up all parts of the pipe to be equal. And do you see that as we make it smaller, it increases in speed? So we've gone from 1.6 meters per second, I believe is what we were at first, to 3.5 meters per second because the pipes are smaller. Anytime you make the pipe smaller, it's going to move at a faster rate. Now, let's also see the pressure. The pressure right now is at 102 kilopascals, and that's with the smaller pipe. And let's see what happens, because we haven't filled this part of our notes out yet. I want us to look and see what happens to pressure as speed decreases. So speed has decreased, and if you look, the pressure has increased, because we started at a pressure of 102 kilopascals, and now the pressure has increased. And the reason why the pressure increases is because the water molecules here have more time, since they're moving more slowly, they have more time to collide with the edges of the pipe, and that creates more pressure in the pipe. So for that last information that we just learned, the fluid pressure decreases as speed increases. And we saw it the opposite way. We saw that fluid pressure increases as speed decreases, right? So this was an example of something that's inversely proportional. We talked about directly proportional and inversely proportional in the last video. Fluid pressure and speed of the fluid is going to be inversely proportional, because as one increases, the other decreases. Now we're going to look at the behavior of gases. Gas laws always affect three properties, or include three properties of a gas. The first one is pressure, and it's measured in pascals, or like we just saw on the pressure monitor that we read, it was kilopascals. The second area that it affects, or property affects, is the temperature of the gas, and then the volume of the gas. So all three of these are included in gas laws. There are three gas laws. We have Boyle's law, which means that you keep the temperature the same, but you're going to change pressure and volume. Charles' law, that says that pressure remains the same or stays constant, but you're going to change the temperature and volume. And Gay-Lussac's law, that says volume is going to remain constant, but you're going to change the temperature and pressure. Now there's an easy way to remember this, because you do need to know these. And there's an easy way to remember these. And let's look at that. We're going to pretend that Boyle, Charles, and Gay-Lussac, they're all going to watch the big fight over at somebody's house. To remember what Boyle's law is, you remember that Boyle wants to bring the pay-per-view to the game. You remember that Charles wants to bring the TV to the game, and Gay-Lussac has decided to bring the party trays to the game. Now, whatever they're not bringing is what is remaining constant in the law. So if you'll look, Boyle right here is bringing pay-per-view, so that's pressure and volume, PV. That means temperature is remaining constant, because he didn't bring anything with T. Charles is bringing the television, which is TV, so he has pressure remain constant, but he's changing the temperature and volume. And then Gay-Lussac is bringing the party trays, or PT, to the fight. And so pressure and temperature are going to change, and he's going to keep volume constant. So this is just a little way that you can remember. You don't have to use this, but it is one option on how to remember which gas law is which. And now I want us to look into an example and a simulation of how these gas laws work. Now, this is going to be a simulation that helps you understand the gas laws, and we're going to keep temperature constant first, and that's going to show us Boyle's law. So this will be Boyle's law. I'm going to go over here, and I'm going to crank out. This is an air pump, right? So I'm going to pump gas into this container. So I pump gas into this container. Volume of the container, I can change if I want to. I can make the volume of the container larger, okay? And I can make the volume of the container smaller. Now, you're going to see the temperature changing here, but if you'll watch it, all it's doing is it's changing to make itself back to the around 670 Kelvin, okay, or 660 Kelvin. It's trying to stay in that range. So as I increase something, it may increase or decrease temporarily, but it's going to go back, and you're going to see down here it will heat or cool itself to get back to the constant temperature. Now, so we have put in a certain amount of gas. It's now reading a pressure of 0.45 atms, which is another way people read pressure. We're going to do kilopascals or pascals, but that's all right. We can use atms at this moment. So it has 0.5 atms. Now, let's say I increase the volume and I make the volume of this container bigger. As I increase the volume, you see the pressure has decreased. So for Boyle's law, as I increase volume, pressure decreases. Let's decrease the volume of the container. So if I decrease the volume of the container, see how the pressure has increased? And what happens to a balloon if you put too much gas in it and it has too much pressure? Right? What happens to that balloon? It bursts, just like this is going to burst. Okay, now we're going to look at Charles' law. Charles' law has the pressure remaining constant, so I changed it up here in our constant parameter, but temperature and volume are changing. Now, I'm pumping in gas into this container, okay, and so it's going to have to get settled here. And the pressure, for Charles' law, the pressure wants to stay the same. So it's going to want to stay close to 0.56. Evidently, it's trying to stay around this area or range, okay? Now, as you're going to see, as I increase temperature, you're going to see the little man pushing the volume. The volume of the container is going to increase. As I decrease temperature for this gas, if you'll look, the little man walks the volume of the container and he's making the volume of the container smaller. So as I increase temperature, volume is increased. As I decrease temperature, volume is decreased. So this is also directly proportional like we've talked about before. Now let's reset this, and now let's talk about Gay-Lussac's law. This is where volume remains constant. So look over here, I can't change the volume. Usually I can change it back and forth with the handle, and I can't change it. They've taken that away because volume of the container is going to remain constant, but we're going to see how the pressure and temperature are related to one another. So let's go ahead and pump some air or some gas into our container and let it get settled. And we're going to see where the pressure evens out at once it gets measured. Okay, so it's going to even out about 0.50. Now, as I increase the temperature, what happens to the pressure? The pressure begins to rise. As I decrease the temperature, the pressure also decreases. So as you can see, the Gay-Lussac's gas law is also directly proportional. As one increases, the other increases. As one decreases, the other decreases. All right, so remember to look over these gas laws. We need to be familiar with them. We are going to work with them in class because there's actually some calculations you can do with these. So we're going to practice those in class. And for your summary, this is what I'd like you to do. I would like you to draw two pictures. One picture that represents what we discussed about fluids, and I would like you to draw one picture that discusses that summarizes what we discussed about gas laws. So do your summarization in pictures today. If you need to, you can use the back of your notes or another sheet of paper. That's not a problem. Have a great evening.